Welcome to today's webinar, Your PDN Gives Your Board Life. Again, my name is Brittany and I will be your moderator. Now, before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you're unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we'll do our best to resolve any issues. Everyone's line is currently muted and will remain so throughout. This will be an interactive webinar with a few poll questions popping up throughout the presentation. Please take a moment when the poll questions are launched to provide some feedback to help us provide you with the most useful information in the future. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We'll have representatives ready to answer your questions directly during the webinar. This webinar will be recorded and posted on the EMA resource page. We'll send everyone who has registered for today's webinar an email with a link to the recording in the next couple of days. And now I want to thank you all for joining us for today's webinar and introduce you to our presenters, Matthew Harms and Roger Chin. Matthew has been with EMA as an applications engineer since 2003, specializing in design side issues pertaining to part management, circuit simulation, and signal and power integrity. Roger Chin is a field applications engineer who has been with EMA since 2013, focusing on component library management, design data management, spice simulation for circuits, and power integrity. To start off the webinar, Roger will give an overview of PDN and some common issues, and then Matthew will follow with a brief demonstration. Assuming we have time at the end, we'll field some questions in a formal Q&A. Now over to you, Roger.
Thank you, Brittany. My name is Roger, and the key question for us to answer today is, what is power integrity and why does it matter for us? So power integrity is essential for our board design. Are we able to bring the appropriate and desired power to our loads? Our first step in understanding power integrity is the PDN, the power distribution network. The PDN is a path that our power will take to get to our loads. We start here on the left with our yellow voltage supply source, the VRM, and we're going to encounter some obstacles that we'll go over in our slideshow today, which we'll call impedances on our way to our load, the die here. So our goal for today is to achieve steady DC voltage at our loads and to minimize the impedances we see between the power and the ground through our operating frequency range. For us to look at the bigger picture first, we want to see how and why power integrity has become more important in our board design. The key factor is that we're dealing with higher speed signals, so our operating frequency range is now higher and higher. And with these higher signals, we now see higher speed issues in power integrity. And we can't approach these problems on a component by component level. We need to consider our board design at a systemic level so that we can catch these issues before we get to manufacturing. Ideally, we'll be able to minimize our power integrity issues and also save time and money. So here on the left, we have our desired PDN behavior. In contrast to the right are what might happen if our PDN is designed without power integrity in mind. We'll go over these in greater detail throughout our slides today, but we want to get home the point that our core PDN behavior is low voltage ripple, little no resonance, or if you have resonance, it occurs at a very high frequency beyond where our board is operating. We want to minimize electromagnetic interference, and we want to achieve all of this while avoiding a spray and pray capacitor placement method. So we can approach this both on the board design side and make improvements for our manufacturing side by avoiding respins and giving us more board space to work with by minimizing the amount of capacitors and vias we put down. When we talk about power integrity, we're talking about power loss. And this power loss is what our noise budget can withstand. And a power loss is composed of our DC power, so our losses, our voltage losses even before frequency, and then in the frequency domain, our AC noise. So down here in the bottom, we have a comparison between poor design and a good design. Oftentimes, AC noise is considered the primary power loss, but while voltage drops are considered secondary. But we have a total noise budget, so if we are able to first reduce our DC loss, we give ourselves a greater AC margin to work with. Let's tackle some of these losses that we might face before we even get into the frequency domain. So DC analysis can be a very useful tool for us for identifying both voltage distribution issues as well as current density issues. And we're going to step through each of these cases one by one and tackle them in the DC side. First, on our power plane shapes, we can see very high current densities as we show here on the image below. And we see how our via pattern in the middle there is causing some very high current densities, some overload of current density almost, because of the way we have it bottlenecking and funneling the path through our shape. In contrast to the right, by simply rotating that via pattern, we give ourselves much lower current densities and avoid dealing with bottlenecking. With BGAs, you oftentimes see this Swiss cheese effect, which might sometimes be unavoidable, but we can identify with DC analysis whether this effect is causing us issues by having so many clearance holes on our power plane. We can also try to avoid some of the Swiss cheese effects by making sure our anti-pads around the vias do not overlap, by leaving any unused pins without a via, and by reducing the number of decoupling capacitors that we might use. Finally, we want to make sure we're avoiding sharp corners, right angles on our power plane shape. A simple 45-degree angle on our shape, we can save a lot by taking us out of issues with high current densities. So these are some tips that we can tackle before we even get into any analysis. But later on, we'll show you how we can visualize whether we are having issues in the DC voltage drops. Now let's step into the frequency domain, which is a little bit more complicated. Our primary tool from the board design side to tackle AC noise is the decoupling capacitor. But it's not as simple as placing down as many decoupling capacitors as we are required from the data sheet. Oftentimes, we need to consider what kind of decoupling capacitor, how many, and where to put these decoupling capacitors as well. Here below, we can see that the second droop and the third droop are the PCB-controlled ripples that we can tackle with decoupling capacitors, which we'll call decaps from now on. So let's step a little higher level and figure out how can we measure whether our board is able to achieve the low voltage ripple we want at our whole operating frequency and at every location on our board. So the measurement for this is the target impedance, that Z target equation at the top here. Typically, the allowed voltage ripple is around 5%, and we multiply that by our power supply voltage, and then divide it by our dynamic current, which is the theoretical current, the total amount of current that might be switching at any one time. So we're able to achieve what we call flat PDN impedance. That means that for every point on the board across our whole frequency range, our PDN impedance is below that target impedance. Let's step into an example where we have some commonly provided data sheet specifications. We have a 5% allowed ripple for our IC. We have a 1.2 volt voltage supply, and our data sheet tells us that worst case power dissipation is 180 watts. So this is not exactly what we have in our equation, but we can essentially get what we need by making an assumption. We can say that the dynamic current is typically around half of the peak current that we might see. And the peak current we might see can be calculated backwards from that worst case power. So the peak current we'll now call the worst case current. So power divided by our voltage supply gives us that current. Plugging that into our target impedance equation, now we can solve for the Z target using a 5% voltage pole, 1.2 volt power supply, now squared, and divide it by that 180 watts. And this gives us about 8 milliohms for our target impedance. So this 8 milliohm is this dashed line that we are theoretically calculating and setting as our goal for keeping our impedance below for our PDN across this whole frequency range. So how are we able to control the impedance in the frequency domain? And that's the simplest way to talk about frequency response is with R, L, and C. So resistance, capacitance, and inductance. So inductance and capacitance are inversely related for impedance. Our inductance increases with frequency and gives us more impedance, so we want a low inductance. Our capacitance should be high. We can store charge on our power plane and quickly provide it for our load, and it will reduce our impedance with frequency. And back to our DC drops, our resistance is always going to, we want that always to be low to give us more AC margin to work with. So in bold here are the decoupling capacitors, which are our primary tool for tackling AC noise. But we want to go in order of increasing frequency here to see what are some other components that affect our impedance on our AC noise. We'll start with the VRM, and then for us on the board side, we're going to work with the decaps, which are composed of bulk capacitors and ceramic caps. And then the power plane itself also has impedance issues. And then beyond our control are the in-package and on-chip capacitors that actually sit on the die. So for the VRM, beyond picking the right VRM, from our board side, we don't have too much to do with the VRM, except understand that it is hugely responsible for controlling the low impedance at the lower frequencies. And it is a starting point for our power supply. So it's very important that we pick an appropriate VRM. And you can see on this plot here, the comparison between the dash line, what it looks like once we have that VRM modeled, and what our impedance plot looks like in this what-if situation if we didn't have a VRM. We're going to focus more on decoupling capacitors today. So again, decaps are our primary tool for tackling AC switching noise. And we have a plot here showing you a variety of decaps covering a wide frequency. Each of those low impedance points are at the self-resonant frequency of the decap. So we have to we have to find out what frequency range we're working within and pick the decaps that are appropriate for providing low impedance within that range. So why do decaps work the way they do? This is because even though they're decoupling capacitors, their parasitics make them behave as essentially a resistor, inductor, and capacitor in series. So I already mentioned the word self-resonant frequency, but that self-resonant frequency is where we see the ESR, the equivalent series resistance, and that's that low impedance we get at that desired frequency. Before that frequency, we see the capacitive behavior, the 1/C. So as we increase the frequency, our decap provides decreasing impedance until we get to the self-resonant frequency. And then beyond that, it actually provides more impedance due to the inductive parasitic behavior. So be aware that when you're using decaps, you are adding more impedance at a higher frequency. And part of where that inductance comes from is the loop inductance that we get from the way the current flows from our power plane here. In the bottom right, we can see this from the VDD up the via, up the fan out to the capacitor, and then down through the via to the ground level. So this loop inductance, as we saw on the last slide, increases our impedance at higher frequencies. So we want this to be as low as possible. And we can minimize this by thinking of where we're placing our vias relative to our capacitors. We want to minimize that via to pad distance. Ideally, we'll put the via right on the pad. But if you can't do that, you want the vias to at least be on the same sides of the capacitor. You can also shorten the fan out and reduce your capacitor height. So back to our very beginning table, we talked about resonance. And just like bridges, power planes can suffer from very destructive resonance if we don't control it. Just like with bridges, which are tacked down by those towers there, we use decoupling capacitors, decaps, to push the resonance of our power plane to a very high frequency to avoid that very destructive EMI. Before we step into our demo, go over again what we've covered so far. So our total noise budget has to tackle both the voltage drops, the IR drops, and the AC noise that we see. We've shown you some tips and ways to look out for our IR drops, as well as how we can use decoupling capacitors to reduce impedance in our operating range and to reduce power plane resonance. But now we're going to show you in our tools how we can visualize and catch these issues from our board directly. So I'll pass it off to Matthew for a live demonstration.
So we're going to start with Power DC. This is one of the two tools that we can offer to solve your power integrity problems. Power DC, as the name implies, is going to start by solving our DC problems that Roger mentioned. There's two aspects to power integrity, DC and AC. We're going to start with the DC aspect, just to make sure we're not losing too much voltage right off the bat. We're not dropping our voltage from our VRM, our voltage regulator module, to our sync devices. So in the board that I have here, I have some shapes. My VRM is over here on my board, and it's supplying current to a sync device over here, a device consuming current. And what I want to do is I want to take a look at what that current is looking like throughout my board, and take a look at what my voltage drop is going to be expected to be over the setup here. And I'm going to go right to load my results from the simulation. The simulation does take about 1 to 2 minutes to run on a board this size. This isn't a terribly big board, but it takes about 1 or 2 minutes to run. I thought we'd just skip past that and get right to the results. So the results come in like this. I'm going to focus on the 1.5 volt plane right here. And you can see the voltage dropping from the VRM supply right here, where it's the highest and closest to 1.5 volts, till it gets down over here to our sync device, where it looks like we've lost about 30 millivolts from our supply to our sync. Where are we losing most of that? You can see pretty quickly from this graph that most of it is lost in this little finger channel, and actually quite a bit here. So we can see our voltage drop from 1.48 down to 1.47. So we're losing almost 10 millivolts right in this little channel, and actually quite a lot here as well too. We can visualize that in terms of voltage like we're seeing right now, or we can even visualize that in terms of current density, which is often very useful. You can see the brighter spots here, the places where you're going to have a higher current density, and higher current density means greater voltage loss, which is what we want to avoid in this case. So you can see there's lots of voltage loss right here where the VRM is supplying, and lots of voltage loss or current density in this area where there's high amounts of current going through just because of a lack of paths for the current to travel. You can zoom in tightly here and see that you're going to have some potential problems right here. So we wanted to know when is our shapes going to turn into a fuse. These high current density areas are certainly good opportunities to be blown up, and that's something that would be a problem that we'd want to avoid. We could try and avoid that by thickening up this channel if that was possible. So if we had space to widen this channel, that would certainly be helpful. And if not, to remove some of these vias, as many as we could, to avoid punching through our plane there. You can also see at the chip here, so if you zoom into the chip, you can see that our current density is not nearly as high comparatively to what it was at the other channel, but you can see we're in the 12 amps per millimeter squared here, whereas previously we're up in 90. You can determine what's a problem for you as well. So what's the threshold that you want to check against? And you can even have that come up as a global plane current density rule. So you can make rules that have these different limits, and then you can get a report back afterwards telling you if you broke it anywhere along the way. So if you broke it at a via or along a plane, it'll highlight those points for you as well. But you can have those type of limits in the tool also. You can see this in terms of vectors as well too. Some people like the visualization that this gives to the colors that we were seeing before. So if you want to see what direction your current is really traveling, you can visualize that as a vector as well too, which is pretty neat to see. Also, you can show hotspots. So as on the window that you're taking a look at, you can show the hotspots showing you where the greatest current density, in this case I'm looking at, is as opposed on this, the window that I'm showing. So 11 is my highest in this. If I zoom out, you'll see that that hotspot will change. Now it's up here, and this spot is the highest with 12. And as I zoom out more, you'll see that this one certainly takes over and becomes the hottest now in the window that I'm taking a look at 92. So that's definitely your hottest spot right there. You can take a look at everything. You can even view your vias as well to see if there's going to be any problematic vias for you also. All right, so that's your DC power. That's how you can take a look when your power plane is going to become a fuse, or where problems are going to pop up on in your DC analysis. You can do with that tool. I'm going to move next to AC analysis. For this, we're going to use a different Sigrity tool, and this one we're going to use for the rest of the demonstration today. So we're going to start off and find out if it matters if our power plane resonates. So Roger was talking about power planes resonating, and if that's a problem, and how it generates EMI and other bad things we don't want. It can interfere with our signals as well too. So we definitely don't want our power plane to resonate if we can avoid it. Right here, what we're taking a look at, I've simplified this board to just my ground and my power. I've taken all the signals out. The green, the power, is this orangish shape, and I'm taking a look at all my layers. So I have a power shape that is about this big right here. And what I want to know with this one is I want to know what type of radiation am I giving off with this power plane, at what frequencies am I radiating it, and that'll help me find my resonances and determine if I need to tack this power plane down at all. So I'm going to do that by hitting View MI Optimization Results. I ran this already before. This one took about 10, 15 minutes on a board this size. This board was about a foot by half a foot, so not a huge board, but not a small board either. And the computer I ran it on is just a laptop, so nothing terribly special. And that takes about 10 or 15 minutes to run to get me these type of results. Let me walk you through what these results mean and how we can interpret them. So first off, the original scheme, I had no decoupling capacitors on my power plane. And under that scheme, here in the top graph, I can see that my cost is obviously low. You can give per unit cost if you want to, or just or accurate pricing for your decoupling capacitors as well too. In my case, I just said the cost is the component cost is what I'm concerned with. If you want to know actual pricing, you can do that as well. But in my case, my actual component cost is nothing, and my impedance is pretty high, and that's my overall performance. So my impedance here, you can see in the lower graph, it's being measured at a bunch of different points. We've turned those power planes into kind of a grid, and we're measuring the impedance at a bunch of different points on that grid. And we're reporting back what the impedance is at a bunch of those points. You can see pretty clearly from this that I appear to have a resonance just under 400 megahertz, about 650 megahertz around there. It looks like there's going to be another one at about a gigahertz. So I have some resonances there that in my power planes that I need to be at least aware of, and maybe I need to change. If I'm aware of them and I don't have problems with them like that, then I might be done at this point. But if those aren't great, then we can start solving this problem by pushing those resonances out. The way we push them out is by using decoupling capacitors. Roger nicely described how a decoupling capacitor is used, and in this case, if we put 2 of them on our board, and it'll tell you which value they need to be and where they go in the report that you can get from this. But we're using one, you can see in the tech tip there, one 100 nanofarad cap and one 10 nanofarad cap, and we're putting those on our board, and it'll tell you exactly where to place them. And you can see that that's starting to push our resonances out. You can see in the dark blue, the red is our original, dark blue is our changed values. We're pushing those resonances out. So we're trying to get rid of those resonant frequencies to clear better space for our signals and to reduce the noise being generated by our power planes, and the overall EMI therefore is going to be reduced as well. If I move this up to 3 decoupling capacitors, so if I can afford to put 3 on, I can push that out higher, and now I'm getting almost to 500 megahertz and 700. So I'm pushing those peaks out, and you could just continue to push them out with 4 components or 5 components or 6 components or 7. And depending on how many you can afford, you might be able to push this out quite far. So if you're really quite concerned with resonances in this power plane, you want to push those out past 800, you can do that with a lot of decoupling capacitors. Or if you're okay like this, you could strike that trade-off of how many decoupling capacitors you want to use versus the type of impedance that you're willing to tolerate at frequencies. Okay, so that's how we can find out if our power planes resonate and how we can do something about that as well if we want to. Another thing we can do, so power planes are good. How about devices? What about our ICs? Can we take a look at those before layout and after layout? We can. So we can take a look at those before and after we lay them out, before to determine which type of decoupling capacitors I should use and what value should I use, and then after to try and figure out how I did and if there's any improvements I could make. So I'm going to start with this one right here. I have a design with just a single device on it, and I want to know where should I put decoupling capacitors and what value should they be to give me the best results that I could expect. I noticed from the poll that most of you just do what the manufacturer says, and that's common with what I've seen as well, talking to customers as well too. They just do what the manufacturer says they should do, and then normally things will work, and that's great. So you can certainly do that. I find sometimes people are either cost restricted, as in they're making a lot of their boards, and reducing costs would certainly save money, and potentially area constricted. So if you're making really small boards, or you don't want to punch those holes in your planes using the vias if you don't have to, those are things where you might want to avoid using so many decoupling capacitors. These are things that we can help with and help you decide which ones you should get rid of. So taking a look at the results for this one, I ran this one beforehand as well. This one took about 2 or 3 minutes to run on my same machine. This is just a single part, so nothing terribly big about it. But what I can do here is I can determine how many capacitors I should use and where I should put them if I choose to use them. So if I can afford 1 decoupling capacitor for this device, it's telling me where to put it. And it's saying you should put it right here. That would be the best spot for it given the type of part that you're using. If you have 2 parts, it might change it. So it might change the 1-part version. If you have 2 parts, it says put them there and there. 3 parts, it adds to that. Notice with 4 parts, it's moving this one around. But every one is independent. It doesn't necessarily rely on the last one you placed. And you're going to kind of strike a balanced trade-off here of how many parts I should use versus what type of performance I can expect to see from this. So this allows you to do a little bit of preload analysis to determine how many decoupling capacitors I should use, what type of decoupling capacitors I should use, and where they should go. You can create reports for this. So if you're doing this independently of the engineer who's designing this, you can generate a report, provide it back to them so that you can give them more than just screenshots. I'll show you a report at the end just to give you an idea of what those reports will look like. Okay, next thing we want to do. Next thing we want to do is do post layout. So what if we got to the board and now we want to do analysis on where things have been placed and we want to know how we're doing on our board. So here's a board that we have, and the IC that we want to take a look at is U17. And I want to take a look at the decoupling capacitors around this board and see how they're doing. So I want to see how those decoupling capacitors are working for me and if there's anything I can do to improve that. So to do that, I'm gonna run the results again, and I'm gonna take a look at the output here. What I'm seeing this time, and this simulation took me about 1 or 2 minutes to run. I'm just jumping to the results again to save time. But what I'm seeing here is I'm seeing a number of different ideas that the simulator is giving me. So it says, okay, I see that simulator chose to optimize for price. I wanted the cheapest price. Cost is the most important metric to me for my decoupling capacitors, so that's what I wanted to minimize. And I want the balance of I want the cheapest cost and I want the lowest impedance. That's what I'd like. In a perfect world, I'd like the cheapest cost, the lowest impedance, and I want to have a kind of balanced trade-off between those two things. So that's what this plot right here at the top is giving us. Cost is your x-axis here, impedance is your y-axis, and we want to get the closest to the origin here as we possibly can. And this blue wave right here is telling us how close we could get. It also tells us how we're doing now. With the setup that we've chosen for this board, how are we doing? And it tells us right here. So your original scheme is costing us 65 cents approximately, and it's given us an impedance of just under 19.5. So something like that is what you're getting. Now what we can do is we can decide, okay, I'd like to do a little bit better. And it gives you options here, different schemes along this wavefront, these different dots or different schemes that it's come up with, a scheme representing a configuration of decoupling capacitors for you that may be better for you. What you can see with each scheme, I'll just click on one scheme right now. So this scheme is the lowest cost. It's going to be approximately the same impedance. I'm not going to see a lot of gain in my impedance, and my time domain isn't going to be much better, but the cost is almost half. So I'm paying almost half what I did for this one. I'm getting nearly the same impedance value. So if you're optimizing for cost and your quality was good enough before, you can now save 30 cents on every board implementing this type of scheme or this type of capacitor scenario and get pretty much the same results. The red here shows your original value, and the blue, I'll zoom in on this. So red shows your original, blue shows your new decoupling capacitor value. This could be a threshold that you want to make sure you don't exceed, and you can take a look at your results here. We've also made it a little easier to turn this into time domain. Most of the time people are thinking more in the time domain and they want to know, what does this mean in the time domain? So you can see your original scheme here is in red, and your modified scheme with the capacitors that we're recommending is in blue. So you can see it's the peak to peak is actually a little higher, so it's probably a little bit worse performance, but it's a little faster. So it's a little faster, a little bit noisier is the trade-off that we're getting with this one. The price savings, though, is huge. What if we chose something else? So let's choose now the most expensive option, which is pretty much the same price as what we're doing right now. But we want to see how that one affects our output. So let's go with one of these here at the end. Let's try this one. So this one here, we're getting hopefully much better impedance performance, paying about the same amount of money. So if quality is the most important thing to you and you're fine with the cost as it is, this is something you could do. The red here showing you the original trace, and the purple here showing you your new modified results. So you can see through this frequency range, this mid-range frequency right here up into the high hundreds or hundreds of megahertz, into the other hundreds, and to the high tens of megahertz. You can see that our performance is drastically improved, and at high frequencies we're about the same as we were before. So this is a big improvement across that frequency range where we have control with our decoupling capacitors. So we're doing much, much better right there. If you want to take a look at how this translates to the time domain, you can see that I'm now shaving some millivolts right off my peaks here. So off the peaks, I'm shaving almost 5 to 10 millivolts off each peak, and I'm much faster as well too. So faster response time, better noise margin. I'm reducing my noise, and I'm paying the same price to get this scheme as I was my original scheme. If this is something you want to go forward with, you can just create a report and you can bring this right back. You can export the scheme data, bring it right into your schematic entry tool as well too. Okay, final thing I wanted to show you. That one here showed you, do I have too many or too few decoupling capacitors? How can I know? That's usually a question that people don't know necessarily how to answer, and it's really hard to answer without a simulation tool to help you out. So hopefully that gives you some idea of how you can solve that. My final question that I wanted to address is how the decoupling capacitor is connected. Is that important? Does it matter how they're connected to the power plane? So what I want to do here is bring you back to the board that we were taking a look at before. This is the same one that we took a look at before. And what I want to do here is I want to just view the capacitor loop inductance. So we want to take a look at that loop inductance. Roger mentioned that in his demonstration, saying how the capacitor gets connected to the power plane through its vias. Does that matter? We want to take a look at that and visualize that. So what we can do here is we can see all of our capacitors graphed by their inductances. So you can see the lowest ones here, the best connections are 2 nanohenries, and some of the bad ones here are 4 times higher at 8 nanohenries. Let's double click on one of those and see why that is the case. So we're going to click on this component here, and C265 has a loop inductance of 8.5 nanohenries. That is a little bit odd until we turn on our planes and our connections, and then it becomes a little bit more clear why that is. So the reason that's happening, we can see, is that our ground over here is connected on one side. Let's turn the vias on too. Yeah, there you can see your connectors. And the power is connected on the other side. And you can see the loop here on the positive side has to go all the way to that via way over, or sorry, I had them flipped. This is ground over here. And power has to go all the way over to here to connect to our power. So that's a long loop, a really long loop, and therefore we have really long loop inductance. So the fix in this case would be to just move your caps closer to that power plane so they could connect, and definitely hit off of your components, use a via much quicker. Don't take so long to get that connection to decrease your inductance. Let's take a look at another situation I have with some devices up here as well too. So here you can see a similar thing. Let's highlight on these C190, that one's red, indicating that it's got high loop inductance as well too. And this one we decided to share a via for all these decoupling capacitors. Just draw a line between them on, I believe, the bottom layer is where they're mounted, and then use the via to come connect. I guess this is power too. So come connect to their power right there afterwards. So instead of bringing it out individually, we've kind of chained it along and drawn them all together. So that saves holes in your plane. It saves some space, but the cost is that your mounted inductance is dramatically decreased. So the effectiveness of that component is really much worse, and that's going to increase your high frequency noise because your impedance at high frequency is going to be diminished. So that's something that we can now identify, and we can determine that, yes, how your decoupling capacitors are mounted does matter. It does have an effect, and you can quantify that effect and see how that is going to affect your output. you can measure all your other devices as well too and see how they're doing. And you can even try different scenarios. You can say, well, how if I connect it like this, what type of mounted inductance am I expecting to see? And you can get a good idea for what you can expect given different setups. All right, so I wanted to go through there. Hopefully I answered most of the questions that were in the invitation, and hopefully that's a bit more clear to you. I'm going to give it back to Brittany. I think she has one more poll question for you, and then we might have some Q&A time.
Awesome, lots of good information there, Matthew. Thank you. And at this time, I'd like to open the floor for the Q&A. So please enter any questions you have into the chat now. If we're unable to address your questions immediately, we'll be in contact with you. And we'll start off the questions with, first off, can you bring in any type of board file to these tools?
Sure, I'll answer that one. You can. So you can, I didn't show you the import. I just had it all set up in the tool already just to save time. But you can bring in board files from our tools, that's the Cadence tools, as well as many other tools in the industry as well too. We accept the ODB++ import and the IPC 2581 imports as well. Those are manufacturing exports that you can export from a majority of tools that exist. So you can bring those right into our tool and start your analysis in our tool from any board format.
Okay. Next question here. Does via sharing for decaps help in improving the power integrity issues?
Yeah, I can take that one too. So good question. The via sharing for decaps normally doesn't really help for decoupling capacitors. You usually want the vias to be individually for each decoupling capacitor. You can, so there's some examples right here where a via is shared. Normally that's not really better. You would like those vias to be as close as possible. The benefit is for space saving and reduced holes in your planes and reduced vias used. So the benefit is that you're reducing that. The detriment to your power integrity is that it increases your loop inductance, which is not desirable.
Okay, and it looks like another one about vias here. It says, can the via inductance be added to the decoupling caps?
So the via inductance be added to the decoupling caps via inductance. I'm not sure. That's a good question. We'll have to get back to you on that one after.
Okay, we will definitely email you with the answer to that once we find out more. Moving on here, what type of setup is needed to make this process work?
So the setup that's needed, we showed a number of different processes today. So for power DC, for our DC analysis, that one, you need your board file, of course, you need your VRM source, and you need your sync currents. Those are the majority of things you need. There might be other things here and there depending on your setup that you'll need. For optimized PI for the decoupling capacitor analysis that we're doing, again, you need your board file and you need some decoupling capacitors. We do have quite a large supply of decoupling capacitors that are available to us in the tool. So we have, I think, thousands of decoupling capacitors from a variety of manufacturers. So you can use our decoupling capacitors. You don't have to import them directly from the manufacturer, but that's the extent of what you'll really need. These tools don't require really a ton of setup. There's not a lot of expert knowledge that you need to run them. You can pretty much bring your board in, attach a few things, and be off and running pretty quick.
Okay, and it looks like on that point of setup, there's a question here for, is this a post-layout analysis only, or is there pre-layout planning available as well, such as like the ones for SI tools?
Sure, yeah, good question. So we did show one pre-layout thing where we had a component that was that we wanted to take a look at where would be a good idea to put decoupling capacitors around that component. So we did show one example where you can determine where those decoupling capacitors should go pre-layout, so you can make a good post-layout choice or layout choice and put them in a good spot. So yeah, we definitely have some pre-layout tools that are available to help you as well.
Okay, and what is the highest frequency the AC tool can simulate?
That's a good question. I don't know that there's necessarily a highest frequency. As far as the tools we're talking about here with optimized PI, your decoupling capacitors only are useful up to a certain frequency. At certain high frequencies, you really move out of the domain of usefulness for decoupling capacitors on your board, and you move into needing those on-die capacitances or on-package capacitances, those ones that are closer to the source. So you need those capacitances, and those are typically out of the realm of our customer base. Our customers are normally doing printed circuit boards, not ICs. So you're relying on your manufacturer to have done that correctly for you when you get up to the very high frequencies. So theoretically, there's not really a limit of how high we can go in frequency, but practically it doesn't make much sense to go too much higher.
Okay, good to know. Next question here, how do sharp corners on power planes impact power integrity negatively?
Okay, good question. So that was to Roger's slide, right? He had the sharp corner there, and it's, I don't know if it's hard to describe, but it's everything going around a sharp corner wants to focus on that point where it all wants to go. So that sharp point makes it a little bit tougher to get around, and the current density there becomes higher, and the current density is higher, it can become more problematic right at that point. If you kind of round that or make an edge to it, then the current density doesn't get quite as high because it doesn't get channeled into one place quite as badly, so it works a little bit better. It's almost like traffic. If you go down from like 6 lanes to 1 lane, everything is channeled into that, and the density becomes really high, and it becomes problematic. And then if you fan out right away after that, it doesn't help that much necessarily. You want to reduce those points where everything is being focused, where that density gets high, just to allow current to travel more smoothly.
Okay, these are good questions, guys. Keep them coming. We'll probably just answer a couple more here. Next question here, do we also consider the board material when doing the PI analysis?
Yeah, great question. That was one I didn't talk to you guys about, but it's right here in the check stack up. I don't know if you guys can still see my screen, but in this, the stack up does come along for the ride. So when you are looking at when you bring in your board file originally, the stack up comes along with it, and you can definitely do some what if analysis here too. So you can play around with your board materials, your board thicknesses, and various things like that to see how would that affect my output. So yeah, that's definitely taken into account as well and editable in the tool.
Awesome. Well, I still see some questions coming in here today. Thank you for your insight in answering these questions, Matthew and Roger. It looks like we are out of time for today, however. But if anybody has questions that were not addressed during the webinar, we'll be following up with you on an individual basis. I will be closing the webinar now, and we'll be sending everyone a recorded version of today's webinar with the slide deck within the next few days. Thank you for the time in joining us, and enjoy the rest of your day.